Lecture 51, Vector Integration. In that lecture, we discussed the surface integral, how to find the integration over the surface. Now, the surface integral. The surface integral is generalization of the double integral. So, let's suppose we have a surface. So, suppose this is a surface, and let P, we have taken a point P with any point on the surface. So, suppose that's in point P, and on that point P, there is a unit vector at that point, that is n cap, in the direction outward down normal to the surface S at P. So this is surface S and this is a perpendicular direction, that is in unit normal vector. Then the vector F in dot unit normal n is a normal component of the vector F at P, at that point P. Then the integration F vector F dot n cap over the surface S is written as double integral F dot n ds, and this is called the surface integral, or sometimes say the flux of the vector F over the surface S. So evaluate the surface integral. It is convenient to express them as a double integral taken over the orthogonal projection of a surface on the coordinate plane. So suppose that's in surface S and this is the projection of R on xy plane. So here we say R be the projection of S on xy plane, and on that plane the unit vector, that's a unit normal vector, that is I cos alpha, j cos beta and k cos alpha. So here that's an n unit normal vector n, that is it make the alpha angle from the x-axis, beta angle from the y-axis and gamma angle from the z-axis, if that's considered as z-axis. So here the cos alpha, cos beta and cos gamma are the direction cosine of that unit normal vector n cap. So here if we take the projection on xy plane, so the projection of ds on the xy plane, that is dx dy, is equal to, we write ds cos gamma. So we take ds cos gamma, and on the place of ds we replace ds is equal to, we can write dx dy upon cos gamma, and cos gamma is what, it can be k vector dot n vector, because corresponding to z, in position vector corresponding to z is k vector, and that is I, and that is j vector. So we can write k dot n cap. Similarly, if we want to evaluate the double integral f dot n ds, so on the place of ds if we take the projection on xy plane, so we take that's dx dy upon k dot n cap. So that is a use when we take the projection of the surface S in xy plane, and if we take the projection on yz plane, this is a, then we write dy dz upon I dot n cap on the place of ds. So that's in projection of on yz plane. And similarly, if we take the projection on xz plane, then in that case we replace ds with dx dz upon modulus of j dot n cap. So please remember this formula. So the volume integration. So here any integral which is evaluated over the volume is called the volume integration. There are two types of representation. If we have a vector function, so the triple integration is used for the volume integration, and we write the vector f dot dv, or if the function is in scalar quantity, so we write the triple integration that dot dv. So that is representing the volume integral. And here these two forms, if we have an vector f dot dv, so that function, or we say the vector f, that is we get the triple integral f1 of these are function of xyz, that's an f1 is a component of the vector f, f1 f2 f3 are the component of the vector f. So we write I f1 dx dy dz, j triple integral f2 dx dy dz, the vector k triple integration f3 dx dy dz. Or if the function that is what is a scalar quantity. So we just write the triple integral phi dot dv. So in that way we just evaluate the volume integral. Here you are using the triple integration. To understand the concept by the example, if we have a vector f, that is 2x squared minus 3zi minus 2xyj and 4 minus 4xk, then we have to evaluate the triple integral del dot f dv, where v is the bounded region by the plane x equal to 0, y equal to 0, z equal to 0, and the plane 2x plus 2y plus z is equal to 4. So we just first we find that del dot f, that is, first we have to find del dot f is what is I del upon del x, j del upon del y, and k del upon del z, and the vector f, that is 2x square minus 3zi minus 2xyj and minus 4xk. Now I dot I, so we take the derivative with respect to x, so we get 2, or we say 4x plus j dot j. Take the derivative with respect to y, we get minus 2x, and k dot k with respect to z we get 0, so we obtain 2x, that is del vector dot f vector. Now because we have to evaluate the triple integral del dot f dv, so here we take the triple integral, that is 2x, and in the place of dv represent the volume, that is dx dy dz. Now you take the limit of x y z. So here as you see, as if you remember the concept of the triple integral, here the bounded region is what is, suppose this is y, we take the x and z, so x is equal to 0 and y is equal to 0, z is equal to 0 means, and suppose we have a plane, that is plane 2x 2y 2z z plus z is equal to 4, so we have to evaluate in the positive octant, right? And so in the order of integration, if you remember the concept of the triple integration, so we take the limit of z in terms of xy, the limit of y in terms of x, and the limit of x we take the constant, or you also change the order of that. So the limit of we can say z varies 0 to 4 minus 2x minus 2y. Now this is the limit of z, and when we take the limit of y, so we put z is equal to 0, so we can say y is equal to 0 to 2 minus x, that is 2 minus x, and x varies, we put y and z is equal to 0 here, so we can say x varies 0 to 2, so that's the limit of x, that's the limit of y. Now you just take the integration and you get the value, that is 8 by 3. The very simple integration, you can easily simplify that integration. Next example, if we have a vector a 2x z I x j minus y square k, so we have to evaluate the triple integration a vector dv, where v is what is the bounded region by the plane x equal to 0, y equal to 0, x equal to 2, and y equal to 6, and z varies from x square to z equal to 4. So here simply we have to integrate triple integral vector a dv. We write the triple integration, that's in vector 2x z I x j y square k. and on the place of dv we write dx, dy, dz. Now here the limit of x is what? 0 to 2, and the limit of y is 0 to 6, and z is varies from what? X square to 4. So now we just take the integration here. So first we take the integration with respect to z. That's the limit of z, which is in the terms of x. So 0 to 2, 0 to 6, and when we take the integration of that vector, so we get 2x z square by 2, that is x z I, and x z j y square z k. We put the limit x square to 4 dy dx. So 0 to 2, that is the limit of x, and now the limit 0 to 6, we get 0 to, we put the limit, upper limit, that is we write 4x I minus 4x j minus y square 4y square k, and minus the lower limit, that would be x cube x into x square I minus x square x cube j and minus x square y square k, and we write dy dx. That whole, or now simplify 0 to 2, that is 4x minus x cube 4x minus x cube I, and here minus 4, and we get plus 4x plus x cube j, and get minus 4y square, and that will be plus, so we write minus x square y square k vector. That's now dy dx. Now again we take the differentiation integration with respect to y. So 0 to 2, that would be 4x minus x cube y I 4x plus x cube y j, and minus that term we get y cube by 3, so we write 4 by 3 y cube, and x square y cube by 3 k, and dx we apply the limit is 0 to 2. So here you see the limit is applied on that term, so we get 2, 0 to 2, that is 2 4x minus x cube I minus 2 4x plus x cube j, and here we get 4 into 8, that is 32 by 3 minus 8 x square by 3 k dx. Now take the integration with respect to x and substitute the limit, that is 0 to 2, and we obtain the value, that is 128 I 24 j plus 348 k. So we get, that is the value of that triple integration. So here we evaluate that integral in the volume which is bounded by these planes. So you have to remember, we have to evaluate the value of that integral, that is in a vector, in the particular volume which is bounded by these surfaces. So then in that example, we have given a function phi. That's an scalar function, and we have to evaluate the triple integration phi dv. And here v is what is in volume, or we can say the region which is bounded by these planes. And here we have to evaluate that integral phi dv. So first we substitute the limits. So here, because the region is what, x equal to 0, y equal to 0, and z equal to 0, and that plane 4x plus 2y plus z is equal to 8. So the lower boundary, first we write the limit of z. Z varies 0 to what we can say 8 minus 4x minus 2y. And when we write the limit of y, we can say y varies 0 to, and we put here z is equal to 0. So we get y is equal to 8 minus 4x by 2, that is 4 minus 2x. And x varies when we put y and z is equal to 0. So on plane we can say 0 to 2. So here these are the limit, that's the limit of x, that's the limit of y, and this is the limit of z. And the function phi is what, 45 x square y dz dy dx. That's an order of integration. First we take the integration with respect to z, then y, and then x. So if you take the integration with respect to z, this 45 is constant, so write 45 integration 0 to 2, 0 to 4 minus 2x, that's the limit of y, and we write x square y here, and the integration is z, apply the limit 0 to 8 minus 4x minus 2y dy dx. Now when we put the limit, we get the integration 0 to 2, 0 to 4 minus 2x, x square y, 8 minus 4x minus 2y dy dx, and the limit is 0 to, and when we put the limit 0, we get 0, we get 0. Now take the integration, first you can multiply the term inside this, and then integrate with respect to y, then with respect to x. So when you take the integration with respect to y, first you can simplify or write that term, that is 45 0 to 2, 0 to 4 minus 2x, and we can write x square y 8 minus 4x, and x square 2x square y square dy dx. Now take the integration with respect to y and apply the limit. We get 45 integration 0 to 2, and we get the integral value is x square y square by 2 and into 8 minus 4x, that's some constant term, minus 2x square y cube by 3. So if you apply the limit 0 to 4 minus 2x dx, when you simplify that term, we get simply 0 to 2, and we get 1 by 3 x square 4 minus 2x whole cube dx. And when you take the integration with respect to x and apply the limit 0 to 2, we get 0.28. That's the result, that's the value of that integral. So here what we do evaluate that integral in the region which is bounded by that surface.